Okay, so let's get started. So this week we'll start to focus on vorticity and vortices. So that'll lead it into our first incompressible potential flow section on lift-induced drag. So you've already started vortices and lift-induced drag in unified, right? So potentially you have learned about the trailing vortices from a wing and the induced downwash on the wing and the resulting induced drag. So what we are learning new over here is more details. So today we are going to really dive into, we're starting to why focusing on vortices is useful, and then use a few examples to extend what you understand in unified to see like a little bit more focus on the physics of vortices. Why does that help in understanding the flow field around and especially behind airplanes and in general lifting bodies? Okay, so first of all, I'll use a video to lead you into like why vortices are useful in understanding airplanes. So again, vorticity is defined as the curl of velocity, right? So if you expand on this, we have x and y, z components. The x component is the derivative of uy with respect to x minus, oh actually sorry, it's the opposite. So let me first write down the z component, which is usually what we analyze in 2D. So the z component of vorticity is derivative of uy with respect to x minus the derivative of ux with respect to y. And we'll see like all the curls are this kind of a cross derivative terms, right? So this is a uz, and correspondingly the x and the y components are basically the subtraction of these kind of cross derivatives, right? For the z component, we have dx, so in the x component, we have dy, right? So basically, we can just circle around, and if this has a dy, we have derivative of uy here, right? So over here, it's uz, and over here is dz. So every cross derivative appears except for the dimension, so if you look at the x direction, it has no dx or ux, right? If you look at the y direction, it has no uy or dy. So the second dimension would be derivative of ux with respect to z minus the derivative of uz with respect to x. Okay, and so this is actually there is a lot of vector calculus you can do with this kind of curls, and one of the most important thing to understand just starting from the very beginning is that this kind of vector has zero divergence. Okay, this is by definition there is a this is purely a kinematic relation, meaning that no matter what kind of a flow fields we are in, right, a vorticity has zero divergence. So the divergence of vorticity has to be equal to zero. So what is the physical consequence of that? The physical consequence of that is that there is no end to vorticity in the flow field. What that means is that if a vortex ends at some point, okay, if a vortex comes into a point in the flow field and ends over here, this is an impossible scenario because you can draw a control volume around the end of a vortex and show that the total influx of vorticity into that control volume that encompasses the end of the vortex has to be non-zero. Okay, and by the divergence theorem, the influx is equal to the integral of the divergence of vorticity inside this small volume, right? Which by the this equation, the divergence of vorticity has to be 0. Therefore, the influx of vorticity into any control volume has to be 0. Okay, what does that mean? That means a vortex cannot end in a fluid. It has to either end on a solid body or extend all the way to infinity, just like what we see like in a video like this. So let's look at how a vortex, which is a concentrated filament of vorticity, behaves in a real world scenario. So look at the vortex over here. So let's stop over here, and where does the vortex end? Right, so we see the vortex that's visualized by a mist, right? Like a low density, low pressure, and therefore low density and the low temperature region. That's the core of the vortex. On one end, it goes all the way to infinity, right? And on the other end, it ends on the wing. So this is actually, in particular, this ends on the junction between the extended flaps and the outboard portion of the wing, which has no flaps, right? So basically, the gap between a higher lift region and the lower lift region, that's like on the takeoff and landing scenario, that's where the strongest vortex come out from the wing. And then what is a more important, another important thing, right? One important thing is how a vortex behaves, which like a vortex has no end is one part of it, and we'll look at other part of how a vortex behave. Another important thing about vortices is how the flow field behaves around vortices. So these two combined, if we understand how vortices behave in a flow field and how a flow field behaves around the vortex, by combining these two understanding, we can understand the entire flow field. So now let's look at how the flow field behaves around vortices. And we'll see the airplane is going to pass through a region where the flow is visualized, right? So we can see the rotation of the flow field around this particular vortex. So this lecture is going to be basically focused on these two aspects. One aspect is how the velocity, how the flow field behaves around concentrated vortices. And two is how vortices by itself, what is the how vortices by itself is going to evolve, right? What is the dynamics of vortices in a flow field? So if we can understand both of these components, then we understand most of the vortex-dominated flow fields, which is actually the case for flow fields behind the lifting bodies. Okay, and this, for example, is a general equation that describes how vorticity, right, evolves in the flow field. We'll dive into this a little bit later. But first of all, let's define what is vorticity and what is circulation. Okay, vorticity, as we said, is simply the curl of velocity, right? So you can see some places use V to denote the velocity vector field. Sometimes we use U. So you should be familiar with both notations. And the physical significance of vorticity is the following, right? So if we are able to put a little bit of a marker in the flow field, and in particular, let's just use a bunch of markers that forms a cross. Okay, so just imagine put a little bit of a dye in the flow field, and that forms a cross, and we'll let the dyed flow evolve with the movement of the flow field. Vorticity essentially tells us how this cross is going to rotate. Okay, so it is going to tell us of, let me just to illustrate several scenarios. So this is, for example, at t equal to 0, the fluid, the dyed part of the fluid forms a cross. Okay, the simplest scenario is that after a little bit, the cross is going to be rotated a little bit. So let's say t equal to a epsilon after a very small amount of time. What this means is that the velocity that's above the center of the cross is going to be higher than the velocity at the bottom of the cross, right? So what does that mean, right? Otherwise, the tip is not going to be tilted in the right-hand side, right? So what does that tell you about the partial derivatives of the velocity? Right, so the fact that this point has moved to here while this point has moved to here, right? Means, yes?
According to the increasing the y direction,
yeah,
positive partial derivative of the x velocity, which is causing the flow field to shoot this way.
Good. So that means a positive partial derivatives of the x velocity. Let me use v here because I think I used the v here. So partial derivative of vx with respect to y. Great. How about here, right? The horizontal line has also tilted. So that means there is again a relative velocity, but in the vertical direction, right? When the fluid particles is separated apart in the x direction. What does that mean for the partial derivative? Somebody, yes.
According to the x direction, the y velocity
yeah,
has a negative partial derivative because the higher x values to the right are more negative.
That's right. So that means there is a negative partial derivative of y velocity, right? We are drawing arrows in the y direction. And the more my x is, the less my y velocity is. So that's why we have a negative y velocity. So combined with these two, right, from my definition of velocity, that means my omega z, which is defined as partial vy partial x, right, minus partial vx partial y, is going to be what? It's going to be negative, right? Okay, so from this analysis, you can also see several corollaries. So for example, if my cross has not been rotated in that way, but like the other way, right, then my omega z is going to be positive, right? So a positive omega z means a rotation in the counterclockwise direction, which by the right-hand side rule means a vorticity that's coming out of the board, right? So that's one of the corollaries. Another corollary is if the rotation of these crosses are in the opposite way. So if my cross has been rotated to be like that, right? Which means they are not forming a right angle anymore. Instead, the horizontal is rotated counterclockwise and the vertical is rotated clockwise. And if the angle of the rotations are the same, what does that mean? That means both of them are positive or negative, right? So if you subtract them from the definition of vorticity, you get 0. Okay, so whenever you see a cross as not being rotated like a solid body, but deformed as usual can be seen in a fluid, that means the vorticity can easily be 0. All right. Okay, similar, another thing you can see in a fluid is that you still have an x, but the horizontal component of x has shrunk and the vertical component has lengthened. right? That's another type of deformation that has zero vorticity, right? Because both of these derivatives are zero. And in reality, this scenario and this scenario are actually exactly the same, just seen from a different coordinate system. Right? Can you see why these two scenarios are the same? This is because this scenario is simply a 45-degree rotation of this scenario. Okay, so instead of having a cross that's horizontal and vertical, if you had a cross that is 45 degrees, okay, then my purple scenario would be a shrinking of one of these 45-degree lines and the lengthening of the other 45-degree line, right? And my green scenario would be, again, two tiltings, except for a clockwise tilting of this line and the counterclockwise tilting of this line, right? So this is something we can use to understand how a flow behaves. So the only scenario where we do have vorticity is this. Well, if you see like a lengthening and shrinking of different directions, it can mean there is no vorticity. And also, if you see different rotation directions, it also means there might be no vorticity. All right. Any questions on this? Yes.
For the case, like the purple case that we were showing before, does that necessitate that there's zero vorticity, or just that there might be like other factors that would possibly tell this?
Yes. So in the case where there are two rotations, right? That's what you are meaning, right? So if the angle of the two rotations are exactly the same, that means there is no vorticity, right? But if the angles of the rotation is different, then there is going to be vorticity. And also, I'm looking at the scenario where the time is equal to epsilon, a very small amount of time, right? When you have a large amount of time, then you have to really integrate, like solve differential equations to see like the angle of the rotation. In that case, even if the angles are the same, there might be vorticity. All right. Other questions? Yeah, that's a good one. Okay. As we're going to see a little bit later, there is a lot of very good reasons why vorticity in a high Reynolds time but low viscosity fluid like air or water is going to be very concentrated, right? Usually concentrates in a very narrow region. That means we usually use what we call circulation to a lot of times we focus not on vorticity itself, but on circulation, which is a integral representation of vorticity. So circulation is, instead of taking derivative of velocity, it actually takes an integral of velocity along a closed contour. And circulation is going to be quite useful. For example, if you have an airplane and you have a vortex over here, you can take a contour around this vortex, right? So this is the contour C, and by integrating, so we know the flow velocity rotates around the contour. So if you integrate along the contour in this direction, you should get a non-zero contour integral of the velocity. And another nice thing about this is by Stokes' theorem, you can actually say that this contour integral, right, is equal to a surface integral, where S is any surface that fills this closed contour. Okay, it is equal to the surface integral of the curl of velocity dot with the normal of this closed surface, right, ds. And of course, the curl of velocity is equal to vorticity, so this is just equal to a surface integral of omega dot with n ds. So now we can see why this is a integral measurement of vorticity. Okay, so if this, what we usually call a vortex is basically a bundle, right? It is a very slim region in space where there is significant vorticity, while outside of the vortex, there is almost no vorticity. That means when you integrate over this S, so let's denote this with S, only a very small portion that intersects with the vortex itself has non-zero omega in it, right? The rest of the portion, the whole green area minus the small purple area, has 0 omega. So as a result, it doesn't really matter what kind of a contour you draw, right? You can enlarge the contour a little bit, you can shrink the contour a little bit. As long as this contour goes around the vortex, you're going to get exactly the same circulation. And as a result of that, we usually use circulation gamma to denote the strength of a vortex, right? A small gamma means a weak vortex, a very large gamma means a very strong vortex. All right. And another thing is that it also doesn't matter where the surface intersects with this vortex, right? Because a vortex has no end, so it cannot end somewhere. It cannot also become weaker or stronger along the length of it, right? That's because this gamma is going to be the same, right? It doesn't matter what surface you use to close this. The Stokes theorem tells us that no matter what kind of surface we use to close this contour, we should get the same circulation. And therefore, if the surface intersects with the vortex over here or at a different location, it's going to be the same circulation. This is saying that a vortex not only cannot end, it cannot also change its strength along the length of the vortex. All right. Okay, any questions on this? So this is just about the definition of vorticity and vortex, whose strength is going to be measured by the circulation. Okay, now let's see a little bit question about vorticity. Okay, so given the following streamlines for a steady two-dimensional flow, by streamlines I mean the path of the flow. So there is no indication of the velocity or the strength of the velocity, the magnitude, right? It just only shows the direction. And which of these two flow fields are irrotational, which means the vorticity is 0 everywhere? So A or B or both or neither or not enough information? Yes? Not enough information. Why is that? Yes?
We don't know. We know in flow A it's rotating, but we don't know how fast. In flow B we know it's going right, but we don't know how fast. So if the bottom lines of B are going much faster than the top lines, then it's going to have rotation, positive rotation. And the same A, like you can have positive or negative rotation depending on the velocity of the curve.
That's a very good point. It all depends on the magnitude of the flow fields, right? The magnitude of the velocities. So an exercise I'll have you again work on pairs is that can you construct 4 different scenarios, two for each of these pictures. You want to construct a flow field on this one that is aligned with the flow with the streamlines that is rotational and irrotational, right? Non-zero velocity, non-zero vorticity, and 0 vorticity. Also for this scenario, one flow field that has 0 vorticity and another has non-zero vorticity. Yeah, please start working, and I'll go around and collect the answers.
Yeah. Oh,
in a way it's zero voltage.
That's the one I'm expecting.
You can't actually, it's not easy. Because, well, but A has to be rotational, no matter what.
How do we make a different case? Do we write magnitudes or do we just redraw?
You have like infinite quantity at the center, and then like you know.
I'm in the same place with you.
In the same way, a point mass generates similar divergence gravitational modes, except
But would you still call the flow rotation if it has a single point that has
I think it's non-zero.
it's rotation. And I don't see
It's harder to but we're
You can. No, yeah, you can. I mean, unless you have all the curves section like this. And you have another.
oh, I mean there's those rules.
You can get away with a zero in the center, but you still.
So you don't have any point other than the center. You need like the same dimension.
I didn't.
I
I
read
should have done that.
the reading.
Did it help?
It was on lift and drag because I saw the first problem on the iPad and I didn't do it for this.
I don't know how you can make your second rotation.
But it actually should decrease as far as.
Right, to preserve something. Substance. Stokes theorem.
Is there
If you vary the magnitudes in a way.
Oh yeah, but then you're like bending a lot, right?
Would it be bending?
We just have to satisfy this
yeah. I know, like, given the streamline that we're given,
If it is, that's my bad.
There's no divergence, right? It's required to be no divergence.
There could be divergence.
But wouldn't that mean the flow field gets spiral afterwards or because there has to be some.
Oh, it's just what's on the canvas.
Yeah. Yeah.
Oh, so okay. If the velocity magnitude is non-uniform, e.g. in a boundary layer, then du dy does not equal 0 and thus
Talking about with respect to A or B?
with B.
What'd you say?
Yeah.
You have an answer? So what's your thought process?
You could set up the little box. They're all like at the same point, like you're going from same like ambulance.
I'm thinking that if you make E rotational or A rotational, then it has to be rotational.
Yeah, because any velocity at all, even if
What about the other
non-uniform, is still
Yeah, because there's no
Like if the bottom one's going
But
down,
but B is a special case where you can have them all they have the same magnitude.
Yeah, and then that's yeah.
Following the notes. No, this is really helpful.
Okay, so next time read notes before class.
Yeah.
No. I was doing the first problem for the homework, and I was like, I don't know, why is it? How do you calculate the difference between like energy?
You finished it though, right?
Okay, so I see most people worked out the second scenario, right? So the scenario where we have parallel flows, is actually relatively easy because the irrotational scenario is just the Vx equal to a constant, let's say 1, and let's actually use V here. Just let's don't switch notation mid-class. Vx is equal to 1, Vy is equal to 0, right? By the parallel streamlines, Vy has to be 0. And the rotational scenario is actually what typically happens in a boundary layer, right? I still have Vy has to be equal to 0, but Vx, let's say, is equal to y, the distance from the solid surface. That's a typical rotational flow that's seen commonly at the bottom of the boundary layer, where the flow is very close to the wall. Okay? Now, the A scenario is a little bit more difficult. Okay? So it's actually easy to come up with a rotational case. The rotational case can simply be, okay, so first of all, in order to follow these kind of streamlines, we have to have negative, okay, so we have to have positive x velocity when y is negative. Negative x velocity when y is positive, and positive y velocity when x is positive, and the negative y velocity when x is negative, right? So that means one of the simple ways to construct this is Vx is equal to minus y, right? The smaller the y is, the faster the x velocity is. So basically, as y goes more and more negative, the x velocity goes larger and larger. And as y goes more and more positive, the velocity goes faster and faster in the negative direction. And Vy is equal to positive x. That means as x goes larger, the y velocity also goes larger. And as x goes more negative, the y velocity goes more negative. Yes?
Would this be the same as v equals the radius?
Yes. This is exactly the same as saying velocity magnitude is exactly equal to the radius, right? If you take the magnitude of this, square them, add them together, take the square root, that's the magnitude. You're going to see it is equal to square root of x squared plus y squared, which is the radius, right? And the direction is going to be exactly along the circumferential direction. Okay, what is the vorticity of this? What is the omega? It's equal to 2, exactly. So the derivative Vy to x is equal to 1. The derivative of Vx to y is equal to minus 1. So 1 minus minus 1, you get 2, right? Omega is equal to 2. So now the difficult case is the irrotational. As we see that, okay, so omega equal to 2 means if you draw a material cross over here, right? The negative derivative of x velocity means that after a while the vertical line is going to rotate to over here, right? So the vertical line, of course, if it's a very small segment, it almost is a line that follows the streamline, and that's going to keep following the streamline, right? So it's going to curve along with the basically like a circle. And the horizontal line, because the outside is faster, the horizontal line is going to curve in the same way. It's going to become like that, right? So it is exactly what we discussed when we defined the material line definition of vorticity. So if you want to construct a irrotational flow, the vertical line has no choice because I have already defined the streamline, right? So if you have a vertical line, that is already following the streamline, no matter what you do, the vertical line is going to keep following the streamline. So the vertical line is still going to be like that. But in order for the flow to be irrotational, you want the horizontal line to rotate in the opposite direction. You want it to tilt the other way, which means the inside has to be faster than the outside. Right? So instead of the velocity magnitude being proportional to r, I want the velocity magnitude to be something like inversely proportional to r. And you have to go through some calculus to actually figure that out. But this relationship, velocity magnitude proportional to 1 over r, actually exactly works out for the flow field to be irrotational. Okay, so that flow field is, if you write down in Cartesian form, it's Vx is equal to minus y over x squared plus y squared, and Vy is equal to plus x over x squared plus y squared. Okay, so that's a irrotational flow field. And of course, if you look at the irrotational flow field, a interesting scenario is that as x and y, as r goes to 0, the velocity goes to infinity, right? So this is actually a singular flow field in the sense the center is like basically this is a flow field where all the vorticity is concentrated at the very center. Okay? And now one of the interesting things is think about circulation. Okay? Of course, if you think about circulation on this flow field, right, you can draw a box. For a irrotational flow field, the circulation actually integrates to 0 because as you integrate along this direction, so let's draw two boxes. Let's just draw one box. As you integrate along this direction, you accumulate positive integral. As you go vertical, there is no integral, right? Because we are taking the dot product of dl and velocity. And when you go backwards, you accumulate negative integral. And then you go downwards, you get 0 integral. So this section and this section exactly cancels out in the irrotational flow field. But in the rotational flow field, because the velocity magnitude is different between here and here, it does not cancel and we get non-zero circulation. Again, on this flow field, we can integrate along the circle, right? For a rotational flow field, the velocity is proportional to r. So the bigger the r is, the bigger the velocity is, and also the bigger the length of the integral is. As a result of that, the circulation is going to be proportional to what relation of the radius? What? The velocity magnitude is proportional to r. Just to remember, let me copy this. Gamma is equal to integral along the contour, right? Velocity dot with dl. Okay, so here the velocity is proportional to r. The total length of the integral is also proportional to r. So the circulation is proportional to r squared, right? It's proportional to the area of the circle, which makes sense because if you analyze the vorticity, if you compute the vorticity, not here, if you compute the vorticity here is equal to 2, right? So it's a constant vorticity. You are integrating, you either integrate the velocity along the contour or integrate the vorticity inside of the contour. It's the same by the Stokes theorem, right? So if you integrate the constant vorticity of 2 inside the circle, you get r squared as the area, right? So that's consistent. While for the irrotational flow field, the length of the integral is proportional to r, but the velocity magnitude is 1 over r. So it's a constant, right? The circulation is constant. That is why we use the circulation to denote, to quantify the strength of the vortex, because it doesn't matter how big of a circle you draw around the vortex. As long as it is drawn around the vortex, you get the same circulation, right? Okay, here's a conceptual model of a vortex that does not have the singularity. Okay, so the inside of this radius R0, the velocity is equal to actually 1 over, let me use a proper color, is 1 over 2 pi times R. 1 over 2 pi times gamma, which is the strength of the circulation, times R over R0. So this is within what we call the core of the vortex, and the flow field over here is inside of this circle is rotational or irrotational. It's rotational, right? Because the velocity is larger as you go more outside, right? Okay, and at the actually a little bit different from that. Sorry, the velocity is 1 over 2 pi times yeah, that's right. Actually, no, R not squared. R not squared. So that basically makes sure that let me write it a bit clearer over here. So inside of here, velocity is gamma over 2 pi times R over R naught squared. So that is to make sure that when you are at the edge of this core of the vortex, right, R is equal to R naught, okay? And if you integrate around it, you get a length that's 2 pi R naught, right? And the integral is going to be exactly gamma, which is the strength, the circulation of the vortex. Okay, so that's inside of this core of the vortex. Outside of the vortex, we have zero vorticity, right? So that's what we usually define as inside or outside of the vortex. So outside of it, velocity is going to be again gamma over 2 pi, and then we have the radius underneath in the denominator. This 1 over r relationship makes sure that when whatever contour you draw around the vortex, you get the same contour integral, right? And that means there is no vorticity between one circle and the next circle. That's logic. Okay, so this is usually our mental model of what a vortex is like. So in the very center of the core, the flow is rotational, outside is irrotational. So normally if you have a really viscous flow solution, the flow field is not ideal like that. So there is usually a slow decay of vorticity at the edge of the core of the vortex, so like maximum vorticity over here and decays to 0 like over here. But mentally, this is a good idealization of a vortex, or what a vortex looks like. Okay, so let me skip this and leave you as a homework for the airflow around vortices. But like, why is a vorticity useful in understanding flow fields? The two important things is that, one is that we can easily, maybe not so easily at first, but like once you grasp the idea of vortex-induced flow field, you can pretty intuitively understand what the flow field is like around the concentrated vortices. So this is so they call the Biot-Savart law that tells you what the flow field is like around a concentrated vortex. So this is basically you are integrating along the length of this vortex, right? As we said, a vortex has no ends. So you're integrating along the whole length of the vortex. And you're gonna see we have gamma over here. That means the strength of the induced flow is linearly proportional to the strength of the vortex. Okay, and then you have a r, but over r cubed over here. Okay, what that means is that the flow field induced by a small segment of the vortex is inversely proportional to the square of the distance between that point and the vortex. And finally, you have the cross product over here, which means if you have a vortex that's traveling in this direction, right? This is a small length of the vortex dl, and r is the distance between the location of that small segment and the location of the flow field. So dl cross r. So you're going to like use the right hand side law. dl cross r, you get a flow field that's in the direction into the board, right? So you get a flow field into the board like that, and the flow field goes around it. So we're going to exercise that law a little bit more in the next lecture and beyond. So this is basically all we need to know to understand how, if we know where the vortices are, this is going to tell you everything you need to know about the flow field around the vortices. And then there is this law that governs the movement of the vortices themselves. Okay, so and as you can see, the movement of the vortices are determined by both the vorticity omega and by the velocity field, which can be computed by the induced flow field, right? So if you understand the flow field around the vortices, then you can know how the vortices itself is going to move. So let me maybe spend a little bit of time telling you what this equation is about. So first of all, this big D dt is the material derivative. Okay, it is the difference between the vorticity at one point, one location, and one time snapshot, and the next time snapshot, but after the vorticity after the location has moved with the flow field for that moment. Okay, so essentially you're looking at the difference between two time snapshots and two different locations, while the difference in location is determined by how the flow has moved in between these two time snapshots. Okay, and this material derivative can be expressed as a combination of time derivative with a fixed location and a spatial derivative while multiplying the different xyz derivatives by the xyz velocities of the flow field. Right, so this is the first line is a standard material derivative. It's just a law that expresses the material derivative with the spatial derivatives. And the second line tells you how the vorticity itself is going to change as it goes along the flow field. So one of the things, let me tell you first of all, when is this equation correct? Okay, this equation is correct for a compressible flow. So it doesn't assume incompressibility with aligned density gradient and the pressure gradient. So for example, if we have if the density is a function of the pressure, right? That's actually pretty general in different scenarios. For example, if temperature is constant, then density is going to be a function of pressure, right? Or in isentropic flow, right? Density is also a function of pressure. So that is actually true for most of the aerodynamic scenarios we're going to study. And also conservative body force, like gravity, right? So So this is actually true for most of the aerodynamic flow fields. And what's most if you get one conclusion from this equation, the conclusion would be if vorticity is 0, then the right hand side of this equation is 0. Right? There is omega here, omega here. So if omega is 0, the material derivative of vorticity is going to be 0, which means a location with 0 vorticity, right? As you go downstream, the vorticity stays 0. Oh, sorry, I missed something. Like with no viscosity. So right. So viscosity in aerodynamics is usually the only mechanism that generates non-zero vorticity from scratch. So that usually happens near boundaries, right? So that's why boundary layers has vorticity, but outside of it, there is no vorticity. So this class we looked at what is vorticity and what scenarios a flow field has vorticity, and looked at a mental model of a concentrated vortex. So on Wednesday we're going to come over and look at specific examples of the flow field induced by just the trailing vortices from airplanes, right? That's usually a very simple scenario. So we'll look at how the vortices are going to move under its own influence, and also understand the flow field around wingtip vortices. And we'll see basically the small differences between what you learned in Unified and what actually happens in reality, right? So see you on Wednesday.